Imagine a hollow metallic cube whose inner walls are painted completely black, with a tiny hole on one of its faces. If you shine light through the hole, it reflects repeatedly inside the cavity and is almost completely absorbed. The chance of the light escaping back through the hole is extremely small, so the hole behaves like a perfect blackbody. Now, if we heat the cavity, its walls emit electromagnetic radiation. This radiation is continuously absorbed and re-emitted inside the cavity, and a small fraction eventually escapes through the tiny hole. The radiation coming out depends only on the cavity's temperature, not on the material it is made of. This emitted radiation is called blackbody radiation. So, according to classical physics, the electromagnetic waves inside the cavity can have any frequency, and each standing wave is assumed to have the same average energy. Classical electromagnetism also tells us how many standing waves exist for each wavelength. By multiplying the average energy of each wave by the number of standing waves, physicists obtained the Rayleigh-Jeans law, which predicts how much radiation a blackbody emits at different wavelengths. At first, this looked like a great success. For long wavelengths, the prediction matched experiments remarkably well. However, the real problem appeared at short wavelengths. As the wavelength becomes smaller and smaller, the energy density should become infinitely large. In other words, classical physics predicts that a hot object should emit an infinite amount of ultraviolet radiation, implying an infinite total energy, but experiments showed something completely different. The intensity of radiation increases only up to a certain wavelength, reaches a peak, and then rapidly decreases at shorter wavelengths. There is no infinite energy. This enormous disagreement between theory and experiment became known as the ultraviolet catastrophe. It was one of the greatest failures of classical physics and clearly indicated that the classical description of nature was incomplete. In 1900, Max Planck proposed a revolutionary idea. He suggested that the oscillators inside the cavity could not emit or absorb energy continuously. Instead, they could exchange energy only in discrete packets, or quanta. That idea marked the birth of quantum mechanics.